So what we're going to do is develop some equations that describe the different lengths of pipe that will resonate with a specific frequency of sound if it's a closed pipe. So here's what we said in the lab that we did. Here's the results that we came up with. Here's our tuning, here's our pipe, our open pipe. Here's the water. Okay, so this is kind of a solid surface here, relatively solid, it's liquid, but anyway, here's our tuning fork, and it's in the down position, and it creates a compression on this side. Now, one thing that's going to be important later when we talk about open pipes is that it creates a rarefaction, which I draw as little circles that go out into the world like that. But this compression, high pressure air, moves down the pipe. And then it goes all the way down the pipe. And it hits the bottom, and this compression will bounce off the water and go back up the pipe. And so this compression will bounce off, come out, and then it will go out into the world. Like that. Out for our ears to hear. Now, it will resonate, the reflected wave will resonate or amplify or make the amplitude of the sound greater if the tuning fork is in the up position, and it also is creating its own compression that goes out into the world for us to hear, and so it sounds much louder. Now, if the pipe is not just the right length, what happens is that the compression that comes out does not match the compression that's made by the tuning fork. In fact, they can actually work together to cancel each other out. If the compression comes out into the world just as the tuning fork is making a rarefaction, the two can cancel each other out. It'll actually be much quieter than it would otherwise be. But here you have a reflected wave that piles on top of here. Now, when you go from, the tuning fork is actually vibrating like this, okay? I'm going to go super slow motion, but it goes back and forth, back and forth, back and forth. And a complete cycle is when it goes up and down. That's one complete cycle. But here, going from here to here, this is only half a cycle. So we say that the distance traveled by the sound down the pipe and up the pipe is 2L. Okay? But the pipe, the tuning fork only has enough time to go through half of its cycle, which means the sound only has enough time to travel half a wavelength of the sound. And that means that 2 times L will be equal to the wavelength of sound divided by 2. Okay? And so now I can solve for the length of pipe that will resonate, and the length of that pipe will equal the wavelength of the sound divided by 4. This is the first length of the pipe that will resonate with that particular frequency, or with the wavelength created by this tuning fork. Remember, and we can relate the wavelength to the frequency of the tuning fork. Remember that the speed of sound, V, is equal to the frequency times the wavelength. So I can use this equation to make a substitution in here, and I'm going to do that at the end. I'm not going to do that right now. But if the speed of sound doesn't change, it's 343 meters per second for all the different tuning forks, all the different, whatever. But the wavelength does therefore depend on the frequency. If I increase the frequency, I have to decrease the wavelength, and vice versa. All right, now, what if I made the pipe a lot longer? if I made the pipe longer, let me do it over here. Well, what do I have? I have 1, 2, 3, 4, 5, 6. So I'll start with 1, 2, 3, 4, 5, 6 plus 1, 2, 3, 4, 5, 6. Yep, I'm going to do this. I'm going to make the pipe quite a bit longer. And then I'm going to erase the equation I wrote. Right here. I should have put it somewhere else. That's okay. Because here's why this pipe will, if I start with a compression like this, down here, now this is going to go down, and it's going to travel down quite a long distance, bounce off, and come out. But, you know, and this is L. I'm going to call this L2. This is L1, you know, the length of this short pipe. But this longer one, I'm going to call this L2. Okay? And because here's what we're going to give the sound time to do. I'm going to give it enough time so that the tuning fork does the following. It goes up, down, and then back up. So that the tuning fork will then be in this upward position as it vibrates back and forth, creating a compression just as the reflected compression comes out. Now the sound still has to travel through 2L, right? It goes down the pipe and back up the pipe. So that's going to be 2L2, and the L2 means the second length of pipe that will resonate. But now we have to give the pipe enough length to give the sound enough time to travel so that the tuning fork can go up, down, up. Well, up, down, up is 1.5 complete cycles, or 3 halves of a cycle, which means that this sound, when it goes down and back up, is going to have enough time to travel 3 halves of a wavelength. Okay? So when I divide this by 4, I get L2, or divide both sides by 2, I'm sorry. I get L2 is equal to 3/4 of a wavelength. Now, how long is L2 compared to L1? Well, L1 is the wavelength divided by 4. Now, the wavelength isn't changing, right? The wavelength is staying the same because it's the same tuning fork. I'm just changing the length of the pipe that will resonate with it. Well, the wavelength divided by 4 is what L1 is. So what this is going to be is this is going to be 3 times L1. And that's why, and I knew that ahead of time. That's why I said, okay, if this is the length L1, I want to make this, 1, 2, 3 times as long. Now that of course means that you're going to have 2 waves in the pipe. So what it means is that somewhere in here you've got a compression that's on its way up while this one is being sent down. But they just pass right through each other. Remember, waves can just pass right through each other in the pipe. So you can have multiple waves in the pipe at the same time. Well, could I make the pipe even longer? Sure I could. I could just extend this logic. Okay? What if now I can't draw it because there's not enough room on my paper. But what if I made this pipe long enough so that the tuning fork has enough time to do the following? Up, down, up, down, up. Now how many halves of a cycle is that? 1, 2, 3, 4, 5. 5 halves of a wavelength. 5 halves of a cycle means 5 halves of a wavelength is the total length, or the total distance that the sound travels. Well, that means that going up and down the pipe, 2L3, this is the third length that will resonate, is going to be equal to 5 halves of a wavelength. Well, that means that L3 is going to be 5 over 4 times the wavelength. Well, but the wavelength divided by 4 is the first length, L1, so this is going to be 5 times L1. And I can have another length that will resonate. What if I gave it enough time to go up, down, up, down, up, down, up? Now, how many halves is that? 7. So do you see a pattern here? The next L4, rather than go through all the math, is going to be equal to what? 7 halves over here, which is 7/4, which is equal to 7 times L1. So what we have here is we have L1, 3L1, 5L1, 7L1. Now, there is a general way of writing this. Let n equal 1, 2, 3, 4, the positive integers. I can say L sub n, that is the nth length of pipe that will resonate with the tuning fork, will be equal to something times L1, which is the wavelength over 4. So let n equal 1, 2, 3, and 4. So, and this is L1 right here. L1 equals the wavelength divided by 4. Now, what we want here are the odd numbers, the odd integers. What should I put in here to give me odd integers? Now, if you're watching this on video, pause it right now and try to figure out what expression in terms of n am I going to put right here to give me 1, 3, 5, and 7. I want to skip the evens. I only want the odds. How do you get even numbers? You multiply by 2, right? But to get, that'll give you an even number. Now, what is an odd number? It's an even number plus 1 or minus 1, right? An odd number is 1 greater or 1 less. So here's the expression I can use. This is how you get the odd numbers from the positive integers. 2n minus 1. So what is, let's see if this works. What is L1? If n equals 1, the first length that will resonate. Put a 1 in there. What is 2 times 1? 2. What is 2 minus 1? 1. Woohoo! So it's just going to be 1 times the wavelength over 4. Or we can, what about L3? What is L3 going to be? We'll put in a 3. What is 2 times 3? Minus 1? 5. 5/4 of the wavelength. So you have 5 over 4. Okay? So this really works. So you can express, these are the lengths in terms of the wavelength. Okay? So if you, now, I can also express this in terms of the frequency and the speed of sound. If you want to do it in terms of speed of sound, you need to put the speed of sound in there. So I can rewrite this expression here. Let me just make a little room over here. Right, velocity, the speed of sound equals frequency times wavelength. Right, so wavelength equals what? The speed of sound over the frequency. So I can substitute this in there if I want. If I want the length in terms of the frequency, I can do this. So I can also write L sub n is equal to, let me put the 4 over here. This is 2n minus 1 over 4. That'll give me the coefficient out front. And then this is times the speed of sound over the frequency on my tuning fork. So this is kind of complicated, but it's not that bad. Okay? And So if you are a musician, or if you're a musical instrument, or if you want to make a musical instrument, and you want to use closed pipes, and you want pipes that are just the right length to resonate at the notes you want. If you know what note you want, and you know the speed of sound, you plug it in here, and it'll give you the length of the pipe. And it really works. If you want to design a pan flute, which is a very popular instrument in South America, it's a beautiful instrument, you would use this formula to figure out what lengths of pipe you want for either the given notes. Okay. So this is part 1 for closed pipes. Now we're going to do part 2. I'm going to pause this for a second.